Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we are going to give an introduction to linked lists. So in this lesson, we will describe the idea of a linked list, first using students and then using a class. We will then describe a simple variation of a linked list in such a way that you can actually implement it right now. We will add values and nodes into that linked list. We will then consider some of the issues and benefits of this linked list class. This will, of course, foreshadow the linked lists we will be seeing in future topics. Now, suppose I want to remember some numbers. One thing I could do is use this class. So, for example, suppose I wanted to remember 247. Well, what I could do is find a student, say Ollie, and ask Ollie to remember 247. Now all I have to do is remember Ollie, and if I ever needed that number, I could ask Ollie what number was being remembered. Okay. Now, suppose now I want to remember a second number. Now, Ollie already is thinking about 247. So instead, I will find Brooke. So I will tell Brooke to remember 91 and also to remember Ollie. So now all I have to do is remember Brooke. If I wanted to remember both numbers, I would ask Brooke, what are you remembering? Oh, 91. Okay. Brooke, who are you remembering? Ollie. Okay, then I could now go to Ollie and ask, what number are you remembering? And Ollie would respond with 247. Similarly, if I wanted to remember a third number, I could find Casey. Casey is told to remember both Brooke and the number 42. Once again, at this point, all I have to do is remember Casey, because from Casey, I can get Brooke, and from Brooke, I can get Ollie. So all I have to do is remember one piece of information. And with that one piece of information, I can step through this linked list of students to get all of the students. Ollie is the last one, and Ollie does not know of any student that follows. So Ollie is the end of the linked list. I could do this repeatedly as long as I want, and I could have each subsequent student remember the next number, and all I ever have to do is remember the name of the first student. Now here's the clincher. If I forget the name of the first student, then I have lost the entire list. For the first student still remembers the second still remembers the third, but if I forget the name of the first student, I'm lost. Now, each student here is remembering two pieces of information, a number and the next student. This sounds a lot like a class. This class is one that we will call a node. Now, for simplicity, we will simply make everything public for now, and the value that is remembered, it will be a double, and that will allow you to quickly distinguish the value that is being remembered. So any floating point number with a decimal will be a value that is being remembered. But the thing is, how do we store what comes after this particular node? Students would be remembering names. Let us assume that we have an array of these nodes. In this case, we could identify each node with the index at which it is in the array. So this would be a value between 0 and capacity -1. So rather than a student remembering the name of the next student in the linked list, we will store the next index within the linked list, and this will be a value between 0 and capacity minus 1. Thus, we could store our nodes as follows. We could have a capacity that is fixed, say 10, and then we create an array with that many nodes. Now, we will initialize everything to 0. However, we need some way of indicating that currently none of these nodes are being used. We will indicate that a node is not being used by setting its next index to the capacity plus 1. So in this case, that would be 11. So if the next index is 11, that indicates that that node is currently not being used. So initially we have 10 nodes, none of which are being used for our linked list. Now, to remember a linked list, just like I only had to remember the name of the first student, the program only has to remember the index of the first entry of that linked list. So all the program has to remember is one index. We will call that index list head. And to indicate that there are no nodes in this linked list so far, we will set list head to be the capacity of the array. So without coding, let's see what we'd like to do to add 4.3. To add 4.3, we first must find an unused node. Now we're going to assume we have some sort of oracle that can go through this array and find one entry that currently has the value 11 as the next index. All right, so here we have one. This is what the oracle returned. We will set its value to 4.2, and we will set its next index to 10. The capacity will indicate that that is the last node in the linked list. Just like when list head was equal to 10, it indicated that that the linked list had no entries in it. We will then save the value or the index 5 to list head. So now, if we want the first node in the linked list, we just look at list head, and that indicates the first node is at index 5. All right. Then we look at index 5. It has the value 4.2, and its next index is 10, indicating it is the last node in that linked list. Next, to add 9.1 into this linked list, once again we ask our oracle, give us a node. So we have an unused node at index 2. We will set the value 9.1, and we will set its next index to the current value of list head. So this is like me telling Brooke, please remember Ollie, as Ollie was the name I was currently remembering. Having done so, we will then update list head to be that new index 2. Now, let's say we want to add 6.3. Once again, we will ask our oracle to give us an unused node. In this case, we get back index 7. We will then set the value to 6.3, and the next index of that node will be set to the current value of list head, which is 2. We will then update list head to remember index 7. We can now see why this is called a linked list. The list head stores the first index. The first index stores the second index. The second index stores the third index. The third index is 10, indicating that that is the end of the linked list. We could keep on adding more and more values to the front of this linked list. In this case, we could add up to 10. Now, could we program a walk through this linked list? Well, to walk through this linked list, we'd have to walk through the indices of the linked list. So we'll need a local variable of type standard size t. All right, so let us call this local variable index. Now, index is going to be initialized with list head. So we have to keep on going through the linked list until we get to the end of a linked list. And an end of a linked list is when we are at index, when the next index is equal to 10. Well, if list head is 10, that means the linked list is empty. So we're going to have a while loop that keeps going as long as index is not equal to list cap. In this case, 10. So initially, list head is right now 7. Now, we are then going to print what is at index 7. Now, what do we have to update? Well, we have to update the index to be the index that 7 points to. That is, we have to set index is equal to the current node's next index value. So now index is equal to 2. We print what is the value at index 2, and then we set index to be the next index at index 2, which is 5. We then print what is at index 5, which is 4.2, and then we set index to be what is at index 5's next index, which is 10. But 10 is equal to the list capacity, and thus we have finished walking through this linked list. Now, interestingly enough, in fact, we could implement this as a for loop. Here we have a for loop. Index is the loop variable and it's initialized with list head. While index is not equal to list cap, we will execute the body of the loop, which prints the value at the current index. At the end of the execution of each loop body, we update index by setting index to be equal to the current node's next index member variable. So how would you do the following? How could you add, for example, a new value or a new node to this linked list at the end and not at the start? How could you remove the first node from the linked list? Once again, that assumes that there is at least one node in that linked list. How could you remove the last node in the linked list? Also, what happens if you're removing the last node, but there's only one node in the linked list? How could you remove an arbitrary node within the linked list? Say, the node in the linked list that stores the value 7.1. Also, what would you do to the removed node in each of these cases to ensure that it can be reused? All right, you should try to answer all these questions yourself before you go on, because if you can figure this out, it will also help you with the next few lessons, which become a little bit more abstract. So what happens here if we accidentally execute the following code? Here we assign list head the value 0 in the conditional statement, which is a little bit bizarre, but it does actually compile. Unfortunately, what we really meant to do was to compare list head to 0, but instead we made a mistake. We assigned list head the value 0. What has just happened? Well, this is technically a memory leak because we still have 3 nodes, all of which have their next index set to something other than 11. And if we are using 11 as a next index to indicate a node is not being used, then none of these nodes can be used anymore. However, we don't actually have access to any of these nodes. Now, yeah, technically we do. We could walk through the array and set all of the next indices to 11, but what happens if there were 2 or 3 linked lists all simultaneously using the nodes in this array to store values? That's not going to work. All right, so it's even possible to have a memory leak with our simple design here. Therefore, this suggests encapsulation is probably a good idea for a linked list as well. We do not want the user to accidentally change the value of list head. Now, we do have yet again another issue. Once again, we are restricted to the capacity of our array. This linked list cannot go beyond the capacity 10. Well, I guess we could resize the array, copy all the old information over, that sort of thing, but that might be a little bit frustrating. Would it be not better if we could get the memory for each node from the operating system? Yeah, because we can always request a new node. However, that node doesn't have an index, but it does have something. It has an address. The benefit of this is, as long as there's memory available, we can continue to build our linked list. There is, however, one drawback. Asking for new memory is actually sort of slow, but that is a consequence we'll have to deal with. So, following this lesson, you now understand the idea of a node within a linked list. You also know it is only necessary to store the first index. You know that each node is going to store the index of the next node in the linked list. You understand how you can add additional nodes at least to the start of the linked list, and you have a few problems to work out before your next topic. You also know that there are problems with the design we have just described above, and the next few topics will correct those issues. Here are the references, the colophon, and a disclaimer. Cheers!